going to talk to you about error propagation in space, time, and the brain. And once I have my slides, I'll start. So backpropagation through time is one of the workhorses of deep learning, but for now, it is completely biologically implausible, and it is very hard to implement in silico or in biological matter. If you think of only a simple problem, just like the 3 neurons here laid out in space, that's actually already a problem for any kind of backpropagation because, oh, am I pressing here? I didn't want to. Can I go back?
Lower button.
Oh, I'm holding this the wrong way around, possibly. Good. Okay. So if you lay them out in space, you have already the problem that all backpropagation wants a global state. So actually, it would want all these neurons in the same place. But let's put this locality constraints aside, and let's see what actually happens when we solve a temporal problem. If we have a temporal online problem, and then backpropagation through time actually requires a future error to do an update in the present state, which makes it offline. So what we actually do when we do backpropagation through time is that we simulate forward, we wait until we actually have that future error, we roll back to the present state, and then we can update the weights. That usually is what we do in truncated backpropagation as well as in other types of backpropagation where we train until the end, go until the end and then train. A bit of a better situation is with real-time recurrent learning called RTRL. This actually can train online because it requires the present error with a past state, but now imagine it's actually quite storage hungry because it has to remember all the past state up to the present time. So it has to memorize that somehow, and that is not really clear where this is stored. If we look at GLE, this is our framework, we can actually solve this problem with a present error and the present state. So we can actually do all of this local, causal, and online because we don't have to look at the past and the future, at least not in the way RTRL and BPTT do it. Now, our GLE framework is based on 4 postulates. Postulate 1 is that neurons perform 2 different fundamental temporal operations. The first one is one that is well known. It's called retrospective coding, which is the leaky integrator dynamics as you know it. And this causes a temporal lag, as you can see from the sinusoid in blue to the sinusoid in green. The second part of the postulate is this prospective coding. It's the second operator, which is the inverse operator to the retrospective coding. So when they have the same time constant, they can actually cancel each other out. And when we vary these different time constants, we can actually go along the whole spectrum from blue to the red to the green line. So we can vary the shift of our signal. The second postulate is that a neural network can be fully described by an energy function. So what we encode in the energy function is the interneural mismatches as well as the target mismatches. The target mismatch is what you know from deep learning as the target error. And when we use this energy function and don't add any constraint like a target on it, then the whole energy function falls flat, as you can see in the leftmost plot here. As soon as you apply a constraint such as a target or a reward, you see this beautiful energy function, and the neuron dynamics have to follow this energy function. And then once we start learning, we can learn at all times, and we can reduce the energy that is along this path in the energy plane. The third postulate is that neuron dynamics follow a generalized conservation law. This is also what gives us this name of generalized latent equilibrium. For the sake of time, the neuron dynamics, as shown here below, has to remain a bit mysterious. But if we apply this to our energy function, what we basically get is this neuron dynamics, as you can see it here, which is very close to leaky integrator dynamics. And we can also locate all of these different parts of this dynamics in and around the neuron. So we can compute very close to actual neuron dynamics and also close to neuron morphology. The fourth postulate is quite simple. It's basically that we can do parameter dynamics on this energy function. So we take a derivative and then we can adapt all our parameters as we want them. And we also have a microcircuit that implements this. we don't just optimize for something, but we can actually compare it to the correct way to do it. This is the adjoint method, which is the continuous backpropagation through time method. And we're just one operator flip away from that. So what this means then, it gives us the chance to do it online, but at the same time, we just lose a bit of the gain in the error, but the temporalities are all correct. Let me quickly show you some of our results. If we keep the time constants of our both neuron operators the same, we actually get quasi-instantaneous transmission throughout the network. So what we can do is the same thing as backpropagation. Basically, we can solve purely spatial problems, such as cipher 10 or the Higgs boson classification. And in the same architecture, if we vary the time constants, GLE can suddenly solve spatial-temporal problems. Oops, why does it do that? Spatial-temporal problems forming deep convolutions. And we can, I'm not touching anything. Interesting. Maybe I'm doing this wrong here. And then we can suddenly recognize pattern in MNIST. Interesting. I'll put this here. And suddenly we can recognize patterns in MNIST 1D. And we can also recognize patterns in Google speech commands like yes. And then we also try to find out if we can actually scale to wider and deeper architectures. And we can go to 10 or more layers and more than 512 neurons per layer. And we can also deal well with noise in the input and time constants and the rates. And this brings me back to our title, actually. We can perform error backpropagation through space, time, and we also provide a blueprint for the brain and also other hardware. Thank you very much.